Okay, I'd like to review a topic that we discussed a while ago that is relevant for what we're doing right now, and that is electromagnets. So, as we discussed before, a current carrying wire will create its own magnetic field, and the magnetic field lines make concentric circles around this wire. Okay, so this is an attempt at a perspective drawing. Um, I find it a little easier to understand if I draw it like this. If this is the current, then concentric circles of magnetic field lines wrap around this current. Um, in this case, I have one that is coming towards me and one that's going away from me down here. So these are the magnetic field lines where they, if you imagine them in 3 dimensions, this is where they pierce the piece of paper on their way through. So here the magnetic field line is coming out of the paper. Between us and the paper, the magnetic field line is curling down here, and then it goes back into the paper, and then it's behind the paper, and behind the paper it curves back up to this point. Okay, so this is kind of what I attempted to draw here, but I find this version a little easier to follow. And so this is one circle, and then I could draw another one. Right, so this is another circle, another magnetic field loop with a larger radius. Right, and I get these everywhere around this wire. Okay. By the way, how did I know that the field comes out up here and goes in down here instead of the other way around? Well, we can figure that out with the right-hand rule. And I showed you in the past a second right-hand rule. So I'm going to call this one right-hand rule number 2, which is a shortcut to figuring this out. So you do not need right-hand rule number 2. It is supplemental. You can do everything with the first right-hand rule, the one for cross products. But this one is a shortcut if I want to know the direction of the magnetic field around a current. And here's how it works. What I do is, of course, I'm using my right hand, so it's called the right-hand rule. I'm going to take my thumb, and I'm going to point my thumb in the direction of the current. And then my fingers, after I do that, curl in the direction of the magnetic field. Okay, so my thumb, I'm going to point it to the right with the current, and my fingers are curling in the direction of the magnetic field, so I can see by the way that my fingers are curling that it's coming out of the page up here and going into the page down here. Here's another way to demonstrate that. If you imagine that this pencil is a current carrying wire, and the current is going in the direction the pencil is pointing, right-hand rule number 2 is effectively I'm going to grab this wire so that my thumb points in the direction of the current. Okay, so I don't grab it like this. I have to grab it like this so my thumb is in the direction of the current. And my fingers basically model what the magnetic field lines are doing. Okay, my fingers are modeling what the magnetic field lines are doing, which is making circles that go around, and my fingers are pointing in the direction of the magnetic field. Okay, let's do another view. This time, let's have the current coming towards us. What do the magnetic field lines look like for this current? Well, again, they are concentric circles for a current. Concentric circles around the current. Okay, that's my magnetic field lines. Which way do they point? Well, I'm going to use right-hand rule number 2. So pause the video and try this yourself. Remember, here's the recipe up here for right-hand rule number 2. Okay, so let me do right-hand rule number 2 here. I'm going to take my right hand. I'm going to point my thumb in the direction of I, so that means I need to point my thumb so that it's coming out of the page towards me, towards the camera, or towards my face. And my fingers are going to curl in the direction that the magnetic field points. So the magnetic field is going to go counterclockwise around this wire. Okay, and it's pretty straightforward to see that if the current now is going away from us, it's going into the paper. Right hand rule number 2, I point my thumb into the paper. My fingers are curling this way, so the magnetic field is going clockwise now for this one. Okay, so what we've just seen is the core idea behind an electromagnet. Electromagnets are often constructed of coils of wire, and so let me discuss why that is. First, I'm going to draw down here a coil of wire. Okay, here's my rough drawing of a coil of wire. So what I have here is a cylinder. The cylinder could be hollow, for example. It doesn't have to be, but let's say it's a hollow cylinder, and I have wire that's wrapped around the cylinder. Now, usually the wire is wrapped around much tighter and many more times, but it's easier to see if I spread it out a little bit. And then this is all one wire, and these are the two loose ends of the wire. Now, if I connect these two loose ends to a battery, I'm going to get a current going through this wire around the coil, around the cylinder. What direction does the current go? So with this symbol, remember, this is the positive end, and this is the negative end. The longer line represents the positive end. And as before, we're talking about, we're going to focus on conventional current here, so it comes out of the positive end. And here, my attempt at drawing it here is that it goes behind on the way up here, and it comes out up here, so it's coming out up here. Here it's coming towards us as it comes over the top of the cylinder, and then it's going down. And then back here, it's down here, it's going away from us. And then behind the cylinder, it goes up. And then it comes out over here, goes down, goes in, goes behind, comes up, down, in, behind, okay. And then this one, I guess I should connect like this. Okay. Okay, so I've drawn the current as it travels around the cylinder. Now let me clean up this drawing a little bit. I'm just going to focus on, if you like, I imagine I'm taking a slice through the center of this thing, right along the center line. And so I'm just looking at the current as it comes out and goes into the page, right? So I'm going to transfer this to a simplified drawing. Okay, here's my simplified drawing of the coil, where I've taken a slice through the middle. So this is all one current. This is all one wire carrying a current. Here the wire is coming out of the paper. Between us and the paper, it's circling down, and then it goes into the paper. And then behind the paper, it circles back up, and then comes out, goes in, circles back out, and so on. Okay, so this is a single current that's traveling around this cylinder. Okay, so I'd like to apply right-hand rule number 2 to this thing. Let's apply right-hand rule number 2 to each of these currents. Okay, let me start with this middle one that's coming at us. So remember, right-hand rule number 2, my thumb goes with the current, my fingers are going to model the magnetic field. So what does the magnetic field look like due to just this current? Well, it's going to be a circle around the current, and it's going to overlap its neighbors. There's lots of concentric circles around it, right? So I can choose any one. I'm going to choose the concentric circle that passes through the center of the coil. Okay, so this is the center line of the coil. Okay, switch my lighting up a little bit. Hopefully this is a little better. All right, so which way does the magnetic field point on these circles? So right-hand rule number 2, thumb goes with the current, so it's coming out of the paper, and my fingers model the magnetic field lines. So they're going to be curling the same way my fingers curl, which is counterclockwise. Okay, so here's what the magnetic field lines look like. All right, and I can do the same process for the wire next to it. So I'm going to look at the magnetic field line loop that travels through the center of the cylinder. And again, it's going to be traveling counterclockwise. So my B field here is pointing to the right. My B field here is pointing to the right. And I think you get the idea already that this one's going to do the same thing. The B field's going to be pointing to the right. This one's going to have a B field pointing to the right down here in the center, and one pointing to the left up here. Okay. So along the center line of this coil, the magnetic field, due to all these wires on the top, are pointing to the right. Okay. How about the wires on the bottom, the currents that are going into the page? So now I take my thumb and I point into the page, and my fingers curl in the direction of the magnetic field. Now the magnetic field is going clockwise. So this is just like the drawing I had before. Right? If it's coming towards us, the current's coming towards us, the magnetic field lines go counterclockwise. If the current's going away from us, the magnetic field lines go clockwise. Right-hand rule number 2 helps us remember that. All right, so let's look at the magnetic field loop around this wire. Now it's going clockwise, okay? And so what's happening along the center line of the coil? If I'm going clockwise around this circle, it's also going to the right. And same with this one. I'm going clockwise around this circle, and my drawing is getting pretty messy and crowded. But I hope you get the idea that these top wires, these currents that are coming out, and these currents that are going in, they are collaborating, basically, and creating a magnetic field that points to the right inside the coil. Okay, so back to this drawing of my coil. The magnetic field inside the coil is going to the right. So effectively what's happening is the magnetic field is emerging from this end of the coil. And it's entering this end of the coil. Now once it gets outside of these currents, it's no longer being constrained to go to the right. It is now free to start to loop around. All right, so we've created magnetic field lines. And this pattern should look pretty familiar. Right? This is the same pattern of the magnetic field lines of a bar magnet. Okay, so this coil of wire with a current running through it behaves like a bar magnet. This is called an electromagnet. Which end of this electromagnet is the north end? Well, remember with a bar magnet, the north end is the end that the magnetic field lines point away from. Okay, so the magnetic field lines are pointing away from this end of the coil. So this is the north pole of my electromagnet. Here the magnetic field lines are going in to this end. So this end is the south pole of my electromagnet. Okay, so you may be thinking that this was a lot of work in order to figure out which end of this electromagnet is north and which is south. So I'm going to show you a shortcut now. Now we figured out the north and south using the second right-hand rule. And so by drawing these concentric circles around each of the currents and using the second right-hand rule, I was able to figure out that the B field is pointing to the right. All right, but rather than doing that every time, let me show you a shortcut. And this shortcut uses, guess what? Your right hand. So this is right-hand rule number 3. Okay. Remember, right-hand rule number 2 is based on right-hand rule number 1. Right-hand rule number 3 is based on right-hand rule number 2. So they all come back to the same source, which is right-hand rule number 1. It's the one true right-hand rule. These others that I'm showing you are shortcuts. Saves you time and energy to use these. Okay, so here's how right-hand rule number 3 works. It's pretty simple. What I'm going to do is I'm going to, much like I did with the wire that was carrying a current, I'm going to grab the cylinder in my right hand in such a way that my fingers follow the current. Once I do that, my thumb now points in the direction of the magnetic North Pole. Okay, so with this example right here, imagine that this is a 3D cylinder. I grab the cylinder, hold it in my hand so that my fingers curl around the cylinder the same way that the current is curling around the cylinder, and my thumb is pointing to the right. So that's this right end is the North Pole. Okay, so that's right-hand rule number 3. Okay, so one last visual illustration here. I've got an actual coil of wire. And by the way, well, first of all, let me point out, you can see how tightly wrapped this wire is. It almost looks like a solid metal cylinder, but this is a single wire that's been wrapped around this cylinder hundreds of times. I don't know how many times. Sometimes it's marked on the cylinder. And by the way, the name for this, a wire wrapped around a cylinder like this, is a solenoid. Okay, so let's say that this situation is what's happening here in this coil, in this solenoid. So to use right-hand rule number 3, I'm going to grab the cylinder in my right hand so that my fingers go the same way that the current is going around the cylinder. So I don't grab it like this. That would be the opposite, right? I want my fingers to be coming out, going in front, and then going in. All right, and when I do that, my thumb is pointing to the right in the direction of the North Pole.